Welcome to Class Concepts, Object-Oriented Coding in Python. My name is Christopher, and I will be your guide. That title is a bit of a mouthful because this is a three-part course. Releasing all three parts takes time, so depending on when you're doing this course, the other two parts may still be in progress. Links in the notes below will be provided to the other two parts as they become available. The purpose of this course is to teach you about object-oriented coding in Python. The first part introduces you to the basic object-oriented coding structures like the class keyword, how you use it to write classes, and how you associate attributes and methods, that's OO speak for data and operations, with the class. Part 2 teaches you how to use inheritance, a mechanism for structuring classes based on other classes. This mechanism allows you to create hierarchies of classes to correspond to real-world items, as well as providing a way of doing code reuse. Parts 1 and 2 are the how, whereas Part 3 is the why. It concentrates on the design philosophy behind object-oriented coding and introduces SOLID, an acronym that provides guidance on writing well-structured object-oriented software. This is Part 1, Class Concepts, and in it you will learn why you might want to write object-oriented code, how to write classes, what attributes and methods are, and how to use the descriptor protocol. The code in this course was written with Python 3.11. Object-oriented coding in Python has gone through some changes over the years, and so the code presented here won't work in Python 2 without some changes. For the most part, I've stuck with general Python 3, but there is the odd line here or there that uses newer language features. I'll point those out when they occur. Python is a mixed bag and includes high-level concepts from a variety of different language styles. It has procedural coding, that's the straightforward scripting type stuff, functional coding, including patterns like lambdas, comprehensions, and MapReduce, and what this course is about, object-oriented coding. For all three of these, Python takes a sort of loose approach. You can take or leave these features as makes sense for the code you're writing. This is in contrast to languages like Java that are strictly object-oriented, where even Hello World requires object-oriented concepts. If you've never come across the term before, object-oriented coding is an approach where you group data and operations on that data together in a structure. In Python, you use the class keyword to declare just such a structure. The class is used to then create objects. A piece of data on an object is called an attribute, while the operations, like functions, are known as methods. There are a variety of ways of declaring and using both attributes and methods, each with different purposes. This course will show you these differences and how to take advantage of them in your code. Your first foray into the object-oriented world covers why you might want to foray into the object-oriented world. Foray is just a fun word to say. In the previous lesson, I gave an overview of the course. In this lesson, I'll make the argument for the use of object-oriented coding. Who doesn't love a good argument? Let's start by diving right into some code. Consider this small function. It calculates the area of a circle, taking radius as an argument. Whatever units 3 is, the area is 28 of those very same units. For fun, let's say light years. Consider if I wanted to do other things with that circle, I might create a dictionary with some data describing it. This dictionary describes both the circle's radius and its color. If I want to calculate the area, I reference the radius key in the dictionary and pass it into the function. Over time, my code might grow. I might add a function for perimeter. I might also add a square, and passing the length of a square's side into the circle area function wouldn't really give me a logical result. Wouldn't it be great if I could group these kinds of things together? Well, that's the idea behind the object-oriented programming methodology. You use the language's features to group data and operations on that data together. Of course, you could do this just by keeping everything together in the same file, but it would be helpful to have the compiler enforce some of the rules. There's another reason for the object-oriented approach. Let's go back into the REPL and look at some data. Here, I've got a person. The person dictionary has 2 key value pairs corresponding to the first and last name. Let's create somebody else. This is similar, but slightly different. I've got a third property, the ID. Logically, Yennefer is both an employee and a person. If you want the concept of a person to also have a middle name, using data structures like this means making changes in 2 places. This is the second key concept of object-oriented coding, structuring data in a way that is reusable. You also want some rudimentary verification as well. Say I had a function that expected a dictionary with keys for first and last name. I could pass either a person or an employee, and it would work. But if I misspelt first in Yennefer's dictionary, it would fail. Having the language ensure that can't happen is helpful. So not only do you want data and its associated operations together, but you want to be able to structure your data so it can be reused. This is sometimes referred to using the phrase is a. The employee is a person, so everything in person should also be an employee. This mechanism is known as inheritance, where employee inherits the person's attributes. If you did it this way, any changes to the person, like the addition of a middle name, would also show up in the employee as well. Building code this way means better reuse and makes mistakes based on the form of the data less likely. Let's go back to the REPL and look at an object like this in the standard library. This is the POSIX path object from the pathlib module. Examining the object, you see that it is a class. A class is what Python, and most object-oriented languages, calls the template that describes the structure of the data. The class doesn't have any data in it. It merely tells Python the form of the data and the methods that can be run upon it. That's a little white lie, but that's close enough for now. I'll show you the details as the course goes on. The thing that stores the data is an object, which you get by instantiating the class. In Python, and in most object-oriented languages, you do this by calling the class with parentheses. You may have seen this mechanism without thinking about what was going on. POSIX path is a class. Using the parentheses on the class constructs an object. In this case, that construction takes an argument, the name of a file. The result of constructing the class is a new object instance, which I've put in a variable named p. The p object has attributes, which you access using dot notation. The fact that I called that an attribute is quite possibly a gross oversimplification bordering on a lie, but the details about how it works underneath aren't important. Dot notation on a member gives its value, in this case, the name of the file the object was constructed with. The object also has methods. These are like functions attached to the object. You'll sometimes hear people speaking about this loosely, but the strict definition is a function doesn't belong to an object while a method does. Just like a function, you can call a method using parentheses. The exists method returns true if the file the POSIX path object is pointing to exists. In my case, it does not. The general term for both attributes and methods is members, as in the members of the object or class. You can see all the members by passing an object to the built-in DIRS function. That's quite a lot, isn't it? If you scan through here, you'll find both the name attribute and the exists method. Okay, let's review. I started with the POSIX path, which is a class. I then constructed it by calling it with parentheses, passing in demo.py as an argument. This construction is called instantiation. The constructor returns an instance object, which I put in the variable named p. The instance object has attributes and methods. In addition to the regular kind of members, Python also has special members, sometimes called magic members or dunder members. Dunder is short for double underscore, as these special members have a double underscore prefix and suffix. Dunder doc contains the doc string for the object. Yep, you can actually get the documentation associated with the code programmatically. It is kept as a special attribute on the object itself. Get used to me calling this Dunder. Not only is it the slang most Python programmers use, it's much more fun to say. Dunder string is a special method that Python calls on the object when you convert it to a string. If you print out p or pass it to the str string function, Python calls this method, and whatever it returns is what gets printed or converted. The POSIX path class is actually built using inheritance. There is a base class called path that is a general implementation of path-like functionality. The POSIX path and Windows path classes extend path, meaning they are path classes, having all the same attributes and methods as path. POSIX path and Windows path implement Unix and Windows-specific features built on top of the base class. They're the employee to path's person. Let's summarize. Why might we use object-oriented coding? Code often relates to real-world things, people and file paths, for example. Keeping the data for these things and the operations on them together just kind of makes sense. By grouping things in classes, you can reuse the code. The common code to both Unix and Windows file descriptors should be in one place. Only the stuff specific to Unix or Windows should be considered separately. That way, if you find a bug in the common code, you only have to fix it in one place. This is part of the DRY principle, short for don't repeat yourself. Defining classes can provide an abstraction mechanism. That means an object can have a well-known interface that the users of that object just need to know in order to use it. If both person and employee have the first and last name attributes, I can operate on them as if they're equivalent without worrying about what else they contain. This leads to a degree of flexibility. You can build interfaces where the coder doesn't really care about the underlying implementation, as long as the interface is understood. You may have heard the phrase duck typing in Python. It refers to the fact that if it looks like a duck and talks like a duck, you can use it like a duck, regardless of whether it is a swan in disguise or not. A related fancy academic term for this is polymorphism. Poly meaning many, and morph meaning forms. Common example of this in Python, and Unix in general, is file-like behavior. If you implement the file protocol methods, there are all sorts of libraries that can use your object which don't care whether you're reading and writing to the local disk or to some remote S3 server. You abstract the details away and just pass around your duck. Enough abstractness and abstraction. Next up, you'll write some code. In the previous lesson, I explained why you might want to write object-oriented code. In this lesson, I'll introduce you to how to do just that in Python. You saw the POSIX path class and how to instantiate it into an object in the lesson prior to this. That instantiation process is done by calling the class with parenthesis. The constructor call can take arguments, which most often are the initial values for attributes that you want to keep in the object. Python uses a special method called dunderInit, which it calls as part of the class instantiation process. You may hear programmers refer to this as the constructor. That isn't technically correct, but it's similar enough to constructors in other languages that it isn't really worth debating. When you write your own class, you likely are going to need to write a dunderInit method to set it up. All of an object's methods, including dunderInit, automatically get called with a reference to the object as their first argument. When you declare a method, you have to include this argument in the signature. By convention, in Python, this is known as self. Technically, you can call it anything you want. The compiler doesn't enforce the name, but your fellow programmers may beat you, enforcing the convention through a different kind of argument. Let's go revisit our circle from the previous lesson, this time as a class. Logically enough, to declare a class, you use the class keyword. Here, I've declared a class called circle. The colon declares a block, and like with other blocks in Python, everything indented under here is part of the declaration. By convention, the initialization method, dunder_init, is typically included first. As you can see here, the first argument to the method, like all methods, is self. When it is called, it will contain a reference to the object. Remember when I said dunder_init strictly isn't a constructor? This is why. When this method is called, the object has actually already been constructed. It's being passed into the dunder_init to be initialized by you. This is also why dunder_init doesn't have to return anything. The object already exists, and you can do anything to it when it's passed in as self. A true constructor, in the strictest sense, actually has to return the newly constructed object. The second argument here to dunder_init is specific to my circle class, and it's the radius of the circle. Note that the argument being passed into the initializer doesn't mean it's part of the object. To do that, you have to actually assign it to the object. As self is a reference to the object being initialized, you use dot notation to store it. I've gone with the typical pattern of naming the object attribute the same thing as that passed into the method, but there's no requirement to do this. This little chunk of boilerplate code actually kind of annoys me. Pretty much every single class you write is going to have this, and if you've got several arguments, you can have several lines of code devoted to this. I feel like there should be an easier way to do this, but don't quite know what it would look like. This isn't just a Python thing. Most object-oriented languages have a similar setup. So that's dunder_init. How about another method? Pardon the lack of spacing here. Normally you put an empty line between methods, but in the REPL you can't do that. This line is the declaration of a method called area. Like all methods in a class, it takes the self argument, and in this case, no others. The code for area implements the famous πr² formula. Notice how it is accessing the radius stored on the object using self.radius. Again, this is possible because self is being passed into the method and is the object. That's enough for your first class. Let's use it to create a circle object. By using parentheses on the class, I'm calling it. Calling the class constructs an object. Because dunder_init took one argument in addition to self, the constructor here expects a value. If I hadn't put the 3 in this code, I'd get an error. As I did put 3, it gets passed into the constructed object, which then calls dunder_init, passing the argument along. The dunder_init then stores the 3 in the self.radius attribute. Once dunder_init is done, the constructor returns the new object, which I've stored in the variable named small. I can access the attributes on the object by using dot notation. And similar for calling a method. Note that self isn't used in the invocation of this method. Calling a method on an object automatically passes the object to the method. As the area method doesn't take any other arguments, it is invoked without any at all. Let's create another circle. This time the radius is a bit bigger. And you can see its attribute. And of course, I can calculate the area on this one as well. Attributes are also editable. Here, I've set the radius to a new value. When I recall area, a new result is calculated. Similar to the whole self thing, the style you use when you write a class isn't enforced by the compiler, but it is best to stick with known practices. It's easier for someone else to understand your code if you use the conventions that everyone else does. First off, like variables, attributes on an object use snake case. That's all lowercase with words separated by underscores. Class names themselves use Pascal case. That's no underscores, but with capitals on each word. If you're coming from other object-oriented languages, you might be wondering about things like private, protected, and public permission structures. If you're not coming from other languages, these concepts control who can see the attribute or call a method, the object, inheritors, or anyone. Python doesn't really have this concept. It uses a suggested convention based on naming instead. If you are coming from another language, this might seem like a bit of a shock. It took me a little to adjust to the idea as well. I used to write code where I tried my best to protect programmers from themselves, trying to stop them from doing things they weren't supposed to. Python's attitude is a little more permissive. It essentially says, hey, this is dangerous, but if you know what you're doing, we're all adults here. So how do you signal danger? Well, Python has public and non-public members. Non-public members are indicated by putting an underscore in front of their names. This isn't enforced in any way. People using the object can touch these attributes and call these methods, but you're warning them that they're not really part of the public-facing interface and they might change. How intensely you use these ideas is kind of a style thing. I don't tend to use non-public values very much unless there's an important reason why. For example, if I've got two values that must be set together, I might store them with underscores and provide a method for changing them at the same time. I have come across code that's the other way, though. One of the libraries I've contributed to once in a while is called ASCII-matics. It's a terminal-based animation and TUI builder. The core maintainer really likes his non-public attributes. Pretty much everything is non-public, with special mechanisms for exposing the API. I haven't actually had a chat with him as to why, but I suspect he used to write object-oriented code in another language and has carried the habit over. You've already seen dunder init, and I've spoken about other special methods denoted by their double underscores. Key functionality provided by Python in classes is mostly built using these kinds of methods. Although they are a system thing, there's nothing stopping you from using the same mechanism. Do note that how they show up is a bit different, though. Any member with two leading underscores gets renamed. It kind of hides the member. Hides as in makes it less obvious. You can still do whatever you like with it, but you can think of it as an extra special warning. If the single underscore is a note in the manual saying you probably shouldn't do that, this is the sticker sealing your device shut saying voids warranty. The sticker doesn't stop you, but you really should know what you're doing. These special methods get renamed by Python. This renaming is called name mangling. For example, dunder member gets renamed as underscore class name dunder member. Just like with the single underscore, I can get at it if I know the name, but you can't really claim ignorance if you're going hunting for things. This works for both attributes and methods. Next up, I'll dive into the various ways you can associate data with a class, covering more information about attributes.